Let's go.
Okay. All right, so today is my presentation on my findings of the experiments run on the PMOS and NMOS. So there were 4 tasks: transistor characteristics, where I test out the NMOS, transistor level design for the logic gate, the gate level design for the D flip-flop, and the DC analysis and transient analysis of the logic gates. So first is for the transistor characteristics. This is my setup and then my schematic. The width is 1.5 and the length is 250 nanometer. First, for my VGS versus IDS graph, my voltage range is from 0 to 2.5 with a voltage step of 0.01 volts. And my VDS versus IDS graph, I set for my voltage range from the VGS to be 0 to 1 volts and the voltage step to be to 0.2. So I would have 5 graphs. The voltage range for my VDS is from 0 to 2.5 with a voltage step of 0.01. So I would get a good resolution for my graphs. So first for the IDS versus VGS characteristics, this was the graph I obtained. And I got the V threshold at around 0.3 or 0.31 volts, where the current suddenly start rising right here, the yellow arrow. And for the IDS versus VDS characteristics, I identified 3 working region. First was the cutoff mode, when the VGS was under 0.31 volts, which was the threshold voltage, and the triode mode, when which is this yellow rectangle area right here, where the VDS and IDS relationship is almost linear, it's almost a straight line, and saturation mode, where it basically leveled out, which is the green rectangle right here. For my task 2,
go back to the previous one, okay?
Okay.
How do you have the 0.31 in this case? Are you taking 0.31 from previous graph or what?
Yeah, I used it from the previous graph, yes, and yeah.
Okay, next.
So this is my transistor level design for the logic gate. First, this is my NAND 2. This is the schematic, and on the right side, that's the symbol. And this is my test bench setup. I set it so that V1 would go up to 2.5 volts with a period of 100 nanoseconds, and rise time fall time equal 1 nanosecond. V3 is also the same, which is my second source into the second input, but the difference is my period is 50 nanosecond, which is half of 100. So within two period of V1, I should have every single possible outcome and combination of V1 and V3. So okay. That would be
next. Show me the waveform.
This is the result. I labeled it like a truth table so we can compare it more easily. And as you can see, the result is as expected of a NAND gate. When it's when both input is 1, it will be 0, and the rest would be 1. And this is my layout. The width is 4.17 and the length is 8.46. And as you can see, it passed LVS and DRC. For my NOR schematic, it's the same with the schematic on the left and the symbol on the right. And the test bench, the setup is basically the same as NAND 2. I just replaced the NAND gate with the NOR gate. Again, my simulation result, I labeled it, so we can see that it compares how the truth table would, with 0, 0 being the only one with an output voltage. And this is my layout, with the width being 4.67 and the length being 8.68. And again, DRC and LVS checked everything. Nothing came back.
Okay, next.
And lastly, it's the SOR gate. I used the 6 transistor setup, and this is my the symbol.
Okay, let me ask you here that do you understand the schematic?
Yes. The normal schematic for the SOR gate usually consists of 12 12 transistor, but for this one, I basically took the schematic of a NSOR gate, which is this side on the left here, and then I just attached an inverter to it, which makes which make the result how I want it, the SOR gate.
Okay, next.
Yep. So again, the setup is the same thing as the other gates, just replace the middle one, the gate. And my result is how an exclusive OR should be. It's either one of the input, otherwise it would be 0. And again, this is my layout. The width is 7.4 and the length is 10.335 because there's a lot more components in the middle, so it's a little bit bigger than the other 2 gates. And for the third test, for the D flip-flop, I use all of the, I guess I used the NAND and the inverter only. I didn't use the SOR for the schematic of the D flip-flop. And this is the symbol. The test bench is, it's different from the other one. This time I used 200 nanosecond and 60 nanosecond instead, because I wanted a little more resolution so I can zoom in a bit better. So my stop time is changed from 300 nanoseconds to 1,000 nanosecond.
Sure.
All right. So as you can see, it's working as intended. When there's a clock signal on the rising edge, the Q will update according to the VIN, and otherwise the VIN does not get updated. And the Q bar, which is this graph and the second graph, will be the opposite of Q. So it's working as expected. And for my final test, the DC analysis and transient analysis of the logic gates. My first is the inverter. This is the schematic that I use and the setup. So it's basically just a default setup for the PMOS and NMOS for this one. The transistor analysis, I use my period is 100 nanosecond, rise time equal fall time 1.1 nanosecond. The pulse width is 50 minus 1 nanosecond for rise or fall time, and the stop time is 300 nanosecond with a time step of 0.1. A DC analysis, I go from 0 to 2.5 volts with a voltage step of 0. I misspelled. It's 0.01. I add an extra.
Okay, got it. Next.
Yeah. So this is the result. So right now we don't have anything to compare it with, so I'm going to move on to where we have some other stuff. We just have to note the rise time is quite high, and TPR is also quite high compared to the fall time and TPF. So now I use the PMOS that is free micro U, so it's like twice as wide. The other setup is everything is the same, and as you can see here, I highlighted these values. These are the values that change the most. The rise time and the TPR are reduced by almost half compared to the ones where the width is not as wide. So this also the V threshold here, it's also higher and closer to the ideal value, which is around 1.25, because our maximum voltage is 2.5. It should be half of that. So yes, as I said, the fall time and propagation delay fault is basically the same, but it has significantly in reduced rise and propagation delay time. So this is due to this because of an inverter. It's like this, so we can basically construct it into an RC model. So over here, using these formula, we can see that with the width increasing, we will have this formula, which makes beta increase. And since beta is in this formula, the denominator would increase. It being on the denominator means that the R that we get would be decreased. And when we plop it into this graph to find the rise time, we can see that the R decreasing basically means our rise times would decrease by the same amount. Since it increased by double the width, so it would decrease our rise time by around half as well.
Okay, next.
Yep. So for our CMOS NAND gate analysis, this is the setup. I use the capacitor 0.5 picofarad. The length is 250 nanometer and the width is 1.5. So the default I changed back from free. VDD is 2.5 volts as as that's the operating voltage. And I have the two sources. The Vin is VA and VB. And these are the sweeping setup. So the most important is just the step. It's 0.01 to have good resolution, but don't have that too many data points to look through. And the stop time is 300 nanosecond. So this is a sample schematic for one of my transition. So basically, to achieve all of these transition, I just swept either V1. First, I swept only V1 and keep V3 at the VDD, which is 2.5 volt. And second time, I sweep V3 and kept V1 at the VDD. And lastly, I swept both of them to test out all of the transition depending on which input is being used. So this is the result. As you can see, the transition 1 and 2 is very similar, except for transition 3, where the V threshold is increased again. And basically every value is increased by, except for VOL and VOH, VIL and VIH, and V threshold is increased by a noticeable amount. It's not significant, but it's very much noticeable. So because of the setup of our NAND gate, it's by default it's made up of two parallel and 2 series transistor. And based on there's a rule that when a PMOS is in parallel, its effective width is basically increased. So since it has more, I guess it has more room for a electric circuitry to move through. So the BP would be bigger. And the NMOS, because they're in series, their effective length is actually, I think it should be reduced. Oh, okay, so the BN is smaller. Yeah. So again, if there's this formula to find a VM, which is our V threshold, and since the BP is larger, which is down here, and BN is smaller, so and those two factors, and including this to be in the denominator as well, this would increase our VM, which is our V threshold. And since our V threshold is increased, if we these two will be affected as well. Since the V threshold is in the middle, it will determine how far the other two would go out with it.
Okay, move on.
And for the transient analysis, I basically did the same thing. So it was, again, in transition 1 and 2, there's no significant difference. But in in transition 3, there's a notable decrease in rise time and an decrease in rise time and an increase in that should be fall time. That's a misspelling as well. The TPR and yeah, and the TPR is also noticeably smaller, as you can see here. This effect is very familiar with us from our analysis on the inverter. So in the case 2, we saw that when we increased the width by two times, it also decreased the rise time by this amount. So I think when we look at the schematic here, we see that when we apply a voltage, I mean a signal to both input A and input B, we can see that we basically made this two transistor in parallel. So it would be based by the same meaning, it would have twice the effective width. So it would have the same effect as the effect we observe in the case 2 of the inverter. So I think that would explain why our rise time is significantly less than the other one. And also, when we apply both input A and input B here, we also have I'm not sure about this one, but I feel there's a longer path. It's like the effective length is longer towards the output. So that would also explain a little bit higher time in I guess in the fall time here, because it takes more time for the electrons, I guess, to discharge from the wire, since now the effective length of it is longer. But that's
okay.
Also,
but did you draw the schematic corresponding with the 3 different transitions?
The schematic for
Yes. So for example, when you for different transition, then the equivalent schematic gonna look slightly different. Something that I did in the class, and then I did it on the whiteboard.
I did not. I forgot that step.
Okay, got it.
Yeah.
Anything else? Carry on.
No, that would be it.
All right.
Yeah.
Anything special you learned out of this?
I learned about the. I think it's very interesting to learn about how the effective width changes the rise time and how it affects that. I also learned that putting in layout is very difficult. It's
Okay.
just complicated. Yeah.
Right. So we're done here. Okay. I will give you some comments if you can give me some comment about the course, and then that's
Okay.
it. These are the casual comment for me mainly, and that's it. I'll see you today.
All right.
Thank
Thank
you.
you.